4 days from today, on June 30th, the world is going to mark something most people have never heard of. An international day built around one simple question. How much of the sky have we actually mapped, and how much is still hiding from us? The answer is going to surprise you, and not in a good way. Because the day exists to celebrate planetary defense, and the honest version of that celebration is also a confession. A public admission of exactly how much of the danger we still cannot see. By the end of this video, you will understand what that gap actually looks like in numbers, why it exists, and what is and is not being done about it. Let's get into it. Asteroid Day falls on June 30th every year, and the date was not picked at random. It marks the anniversary of the Tunguska event of 1908, when an object somewhere between 50 and 190 meters across detonated in the air above a remote stretch of Siberian forest. There was no crater, the object never reached the ground. It exploded several kilometers up, and the shockwave alone flattened an estimated 80 million trees across more than 2,000 square kilometers, an area roughly the size of a major metropolitan region. The blast is estimated to have released energy somewhere in the range of 10 to 15 megatons, hundreds of times more powerful than the bomb dropped on Hiroshima. If that same object had detonated over a city instead of an empty forest, it would have been one of the deadliest disasters in recorded history. It happened in 1908 because nobody saw it coming. Nobody could have. The technology to spot something like that from space did not exist yet. In 2026, the technology does exist. And that is exactly why this day matters, because the question it forces us to ask is not whether we could see a Tunguska-class object coming today. The question is whether we actually have. In 2014, the United Nations formally recognized June 30th as Asteroid Day, an annual reminder pushed for years by a small group of scientists, astronomers, and former astronauts who had grown frustrated watching planetary defense get treated as a side project instead of a real line item. The goal was never to frighten anyone. It was to get the public asking the same question once a year out loud. Every year since, the same numbers get repeated, and every year they get a little more uncomfortable. So here are the numbers for 2026, and I want you to sit with them because they tell a story that the headlines about close approaches and near misses almost never tell. Start at the top of the size scale, the true civilization enders, the objects a kilometer across or larger. Back in 1998, the United States Congress gave NASA a direct mandate: find at least 90% of these objects within 10 years. NASA took longer than 10 years, but it eventually got there. Today, the catalog of kilometer-plus near-Earth asteroids is believed to be more than 90% complete. That is the good news, and it is real good news. We have found the overwhelming majority of the rocks big enough to end civilization as we know it. We have tracked their orbits, and none of the ones we know about are coming for us. Take that win. You are allowed to feel good about that part. Now move down one tier to the objects between roughly 140 meters and a kilometer, what planetary defense scientists call the regional devastation class. These are not planet killers. They are city killers, country killers, tsunami generators. An object in this range hitting a populated coastline could erase a metropolitan area and kill more people than almost any natural disaster in modern history. And an object in this range hitting open ocean could send a wave crashing into coastlines thousands of miles away. In 2005, Congress gave NASA a second mandate: find at least 2/3 of these objects. That deadline has come and gone. The most recent figures put the actual completion rate at around 40%. For the size class that could wipe out a major city, roughly 6 out of every 10 objects are still completely unknown to us. Not hard to track, not poorly measured, unknown. We do not have an orbit for them, we do not have a name for them. As far as our catalog is concerned, they do not exist, right up until the moment one of them does. And then there is the bottom tier, the size class that actually matches Tunguska, and this is where the day's name stops being symbolic and starts being uncomfortable. Objects in the 20 to 60 meter range, roughly the size of the rock that flattened the forest in Siberia in 1908, are not catalogued at 90%. They are not catalogued at 40%. By the best current estimates, we have found somewhere around 4% of them. 4 out of every 100. The other 96 are out there right now, somewhere in the solar system, on orbits nobody has calculated, and the only thing standing between us and finding them sooner is whether one of them happens to swing close enough and bright enough to trip a survey telescope in the days before it arrives. That number is the entire reason this day exists, and it is the number almost nobody talks about because it does not fit neatly into a headline about a single asteroid with a name and a date. It is a statement about the shape of the unknown, and the shape of the unknown does not make for good television, except tonight it is going to. Here is why the gap gets worse the smaller the object gets, and the physics is almost cruelly simple. A survey telescope does not see an asteroid directly. It sees reflected sunlight, a single faint point of light in a field of millions of other points of light, most of which are stars that do not move. The way these surveys work is by photographing the same patch of sky over and over, minutes apart, and using software to flag the handful of dots that shifted position between frames. That is the entire detection system for every near-Earth object we have ever found. It depends entirely on the object being bright enough for long enough to register. A kilometer-wide asteroid reflects a lot of sunlight. It is bright even from enormous distances, which is why we found 90% of them years ago. A 140-meter object is far dimmer, but still bright enough that, with persistent effort, you can chip away at the catalog over years and decades, which is how we got to 40%. But a 30-meter object, a Tunguska-sized object, is so faint that it only crosses into detectable range when it is already close. Sometimes that means days of warning. Sometimes, as the people who study this field will tell you privately, it means none at all. The smaller the object, the later you see it. And the math on Earth's neighborhood works against us in a second way too. Because smaller objects are not just harder to see, there are vastly more of them. Current estimates put the number of near-Earth objects in the tens of meters range at somewhere around 40 million. We have catalogued a few thousand. The objects that are the hardest to find are also the objects there are the most of, and that combination is exactly why the percentage at the bottom of the scale looks the way it does. A handful of ground-based survey networks are doing almost all of the work here, observatories in Arizona, Hawaii, Chile, and South Africa, scanning the same patches of sky night after night, year after year, on budgets that are a rounding error compared to almost anything else NASA funds. And even with those telescopes running every clear night, objects in the tens of meters range slip through constantly. It is a documented ordinary fact of this field that car-sized and house-sized objects pass between the Earth and the Moon roughly every week, and only a fraction of them are ever actually detected before or during the pass. Most of the time that is harmless, because most of the time they miss by a wide margin and nobody needs to know they were ever there. But it tells you everything about how much of this neighborhood remains genuinely unmapped. If you have watched this channel for a while, you have seen the other side of this story already. You have seen the close approaches that do get caught, the ones with names and dates and live streams. Objects discovered days or sometimes just hours before they pass, confirmed safe, and gone again within a week. Those videos exist because the system worked, because something faint and fast-moving happened to be bright enough at the right moment to trip a telescope in time. What almost never gets covered is the version of that story where the system does not work, where the object stays below the detection threshold for its entire approach and nobody ever knows it was there at all. We cannot show you footage of those, by definition, because nobody has footage of an object nobody saw. The only way to understand how often that happens is through the math, and the math says it happens constantly, every week, just below the floor of what we can currently detect. There is also a tier of this problem that rarely makes it into any of these conversations, which is what happens after detection, not before it. Even once a survey telescope catches an object days out, the size estimate that comes with it is little more than an educated guess. Optical telescopes measure brightness, not size, and a small reflective rock can look identical from a distance to a larger, darker one. The only way to pin down a real size is with radar, bouncing a signal directly off the surface and timing the return. And the planet's radar capability for this kind of work has actually shrunk in recent years, not grown, after the collapse of the Arecibo dish in 2020 left fewer large radar facilities able to do this work at all. So even the small fraction of objects we do catch in time often get tracked with more uncertainty than people realize, right up until the moment they are already past us. This is not a hypothetical problem, and we do not have to reach far for proof. In February of 2013, an object roughly 20 meters across, far smaller than the rock that caused Tunguska, entered the atmosphere over Chelyabinsk, Russia, completely undetected. Nobody saw it coming. It was not on any catalog, it had no name, and the first anyone knew of it was a flash brighter than the sun and a shockwave that blew out windows across 6 cities. Around 1,500 people were injured, almost all of them from flying glass, because they had walked toward their windows to look at the light in the sky and were standing there when the blast wave hit. The object detonated with the force of roughly 30 Hiroshima bombs, and not a single observatory on the planet flagged it in advance. That is what falls inside the gap we are talking about tonight. Not a hypothetical, a recent documented event sitting comfortably inside the 96% of objects this size that we still have not found. So the honest, uncomfortable version of Asteroid Day is this. It is not a day to be afraid of a specific asteroid, because right now there is no specific asteroid you need to worry about. It is a day to be honest about the size of what we cannot see, and once you understand that, a different question becomes far more important than any single object's name. If we did find one tomorrow on a real collision course, what could we actually do about it? Before we get there, one thing needs to be said clearly, because this is exactly the kind of gap that breeds bad theories. A 96% detection gap is not evidence of a cover-up, and it is not evidence that anyone is hiding anything. There is no secret list of incoming asteroids being kept from the public. Every number in this video comes from publicly published NASA and observatory data that anyone can look up themselves. The gap is not a conspiracy. It is a funding and physics problem, plain and unglamorous. The kind of problem that does not trend on its own, which is the entire reason a day like this had to be invented in the first place. The answer to what we could actually do is better than it would have been 10 years ago, and it is still nowhere close to good enough. In September of 2022, NASA's DART mission deliberately slammed the spacecraft into a small asteroid moonlet called Dimorphos, orbiting a larger parent asteroid called Didymos, and it worked. The impact measurably shortened Dimorphos' orbit around its parent body, by far more than engineers had even hoped for, in part because the impact threw out a huge plume of debris that pushed the moonlet harder than the collision alone would have. For the first time in human history, we proved that deliberately hitting an asteroid can change its path. That is a genuine milestone, and it deserves to be treated as one. But here is everything that test was not. It was one mission against one object chosen years in advance specifically because its orbit made the result easy to measure. There is no standing fleet of kinetic impactors ready to launch on short notice. There is no operational deflection system sitting on a pad anywhere on Earth. DART proved the principle works, the same way a single successful lab test proves that water can put out a fire. Nobody has built the fire department behind it, and the physics of deflection makes the timeline problem worse, not better, because a kinetic impactor does not stop an asteroid in its tracks. It nudges its speed by a small amount, and that small nudge has to compound, orbit after orbit, for years before it adds up to the difference between a hit and a miss. The strategy needs years of lead time to work reliably. Compare that to the warning times we just talked about. For an object the size of the one that hit Chelyabinsk, the realistic warning window is days, sometimes none. The one tool we have proven works needs years of runway. The detection system, incomplete as it is, frequently hands us days. Those two numbers do not fit together, and no amount of optimism closes that gap. There is one piece of genuinely good news buried in all of this, and it is worth holding on to because it shows exactly what the system looks like when it actually has time to work. If you watched our deep dive on the closest asteroid in recorded history, you already know this one by name. Apophis, a near-Earth asteroid several hundred meters across, is going to pass closer to Earth than our own communication satellites in April of 2029. It is going to miss us. We know that with confidence because Apophis was discovered back in 2004, and astronomers have spent more than 2 decades refining its orbit down to the kilometer. Because the warning came decades early instead of days early, scientists have had time to plan missions, refine models, and rule out every realistic danger with certainty. Apophis is proof that when an object is big enough to catch early, the system we have actually works. The problem was never the big ones, the ones that make headlines and get their own dedicated coverage years in advance. The problem is everything underneath them, the Chelyabinsk-sized objects, the Tunguska-sized objects, the 96% of an entire size class that nobody has found yet, simply because they are too small and too dark to show up until they are already on top of us. That gap is not invisible to the people who study this for a living, and there is a real effort underway to close it. NASA has a dedicated infrared space telescope in development called NEO Surveyor, built specifically to hunt for the asteroids that visible light telescopes struggle to catch, the dark, faint, city killer class objects that make up most of that missing 96%. Infrared light is the key, because even an asteroid that reflects almost no visible sunlight still glows with its own heat, and a telescope tuned to see that heat can find objects a ground-based survey would simply miss entirely. When NEO Surveyor finally launches and reaches its full operational orbit, it is expected to be the single biggest jump in our small object catalog since the search began, potentially finding more city-killer-class asteroids in its first years than every ground telescope combined has found in the past 2 decades. But it is still in development, still years from full operation, and every year it slips is another year added onto a gap that has already existed since before most of the people watching this video were born. If any of this makes you want to actually see the gap for yourself instead of just hearing the percentages, that option exists and it costs nothing. NASA's own tracking dashboards are public, updated daily, and list every known close approach for the weeks ahead, along with the size estimate and the distance at closest pass. The Minor Planet Center keeps a running list of the same data from the international side. None of it requires a telescope or a background in astronomy to read. Pull either of them up after this video and you will see exactly what we have been describing tonight. A steady, ordinary stream of objects passing by, most of them small, most of them found only days before arrival, a live demonstration of the 4% in motion. So here is what June 30th is actually asking you to think about. Not whether a specific rock is going to hit a specific city on a specific date, because nobody can tell you that, and anyone who claims they can is not being honest with you. It is asking whether a civilization capable of mapping 90% of the objects that could end it has done nearly enough to map the objects that could merely devastate one of its cities. Right now, the answer is no. 90% for the planet killers, 40% for the regional class, roughly 4% for the Tunguska class. 96 rocks out of every 100 in that smallest, most dangerous to a city category, sitting somewhere out there right now, completely unknown, on orbits nobody has calculated, waiting for the day one of them happens to swing close enough and bright enough to finally show up on a telescope, with however many days of warning that turns out to be. That is not a reason to panic. The odds on any single night for any single city remain extremely small, and nothing in this video changes that math. But it is a reason to understand what an awareness day is actually for. It exists because the people closest to this problem do not want it solved quietly, in a budget line nobody reads decades from now, after the gap closes itself by accident. They want it understood by enough people that the gap actually gets closed on purpose, instead of just measured and repeated year after year, while the same 96% sits there unexamined. Mark the date, June 30th. Not because anything specific is coming, because it is the one day a year built specifically to ask whether we are looking hard enough, and this year, the honest answer is still not yet. We will be tracking this as it develops,